We looked at the way to set up internal flow, at least conceptually, but we haven't taken a look at how to actually go through the process of like finding numbers from other numbers. In particular, we haven't been able to develop the workflow associated with finding the H in internal flow, or at least we haven't done so yet. And we're going to find that the process via which we do it is extraordinarily similar to the process that we had for finding heat transfer coefficients in external flow systems, right? And so this is an exercise that will allow us to test our understanding of how internal flow occurs and how we can get, like I mentioned, parameters from parameters, numbers from numbers. So here's the setup. We have this pipe, which has a diameter of 3 centimeters and a length of 5 meters. And through it, we have this liquid, which is pretty close to water, that is flowing at a mass flow rate of 0.1652 kilograms per second through this pipe. And the properties of water at kind of inside of this pipe are roughly represented by the following values. Okay. The water enters at a temperature of 290 degrees Kelvin and is heated up to a temperature of 340 degrees Kelvin by a uniform heat flux that is applied to the surface of the pipe. Okay. And now the question that we have to ask ourselves is, well, what is the net heat transfer rate that's happening to the liquid, right? What is the net heat transfer rate as a result of all of these imposed heat fluxes? And then also, what is the surface temperature of the pipe at the outlet, right? Why would this matter? Well, imagine that you're designing a pipe for heat transfer. If you make it out of plastic or something like that, you have to make sure that the temperature of the pipe doesn't get so large that the plastic doesn't start to kind of melt and deform. And so it might make sense for you to try to figure out what's the maximum temperature, an estimate for what the maximum temperature of that pipe is going to be, which makes sense for it to be at the outlet because that's when the liquid gets the hottest, right? So we want to find this total heat transfer rate, but we also want to find the surface temperature of the pipe at the outlet. How do we do this? Well, let's see if we can't find the Q first. How or what equation can we use to find the Q? Well, there is one nice equation that allows us to figure out this Q as long as we know the temperature of the liquid at the outlet and the inlet. It was the equation that related the net heat transfer rate in from the sides, what we're trying to find, to the rate at which thermal energy is entering and leaving, the system via the fluid. And essentially that equation, which we saw in the last lecture, is just that Q is equal to m dot times Cp times TMO minus TMI. Right? The rate at which the thermal energy leaves via advection has to be compensated for by the amount of thermal energy, or the rate at which the thermal energy enters through the sides. We know the m dot, and we know the Cp, and we know TMO, and we know TMI, so this is just a single line of calculation. We never have to worry about finding H's. We never have to worry about calculating Prandtl numbers or Reynolds numbers or anything like that. This equation gave us everything. Now, we are not always going to be in a position where we have these two temperatures, but it's quite nice that we can make this relationship, that we can find this Q as a function of these two things, or to find one of these things as a function of Q and the other one, without ever having to go through that kind of maybe tiring, cumbersome workflow of looking for H's. Okay? So if I actually plug those numbers in, which in the interest of time and brevity, I'm going to save you the effort, what we would find from that single line of calculation is that the heat transfer rate through the system is approximately 34,518.54 watts. So one line of calculation, right? So about, this. Now that we have the Q, well, can we get any information about TSO? Well, if this is the Q, right, we can also use this as long as we know the diameter and the length. We can use the geometric properties to find the Q double prime. Because remember the Q double prime, in a scenario where the Q double prime is constant, is just the Q divided by the surface area over which that heat flux is being applied, which is in this case just Q divided by the length of the pipe times the perimeter. What's the perimeter of a circle? Just pi times the diameter. Right? And so we know the Q, we just found it. And so we can find the Q double prime via this relationship, which once again, I'm just going to skip actually writing down the numbers. You can feel free to verify it. And we find that the Q double prime is approximately 73,287.77 watts per meter squared. There we go. Why does this matter? Well, remember that the Q double prime in a system like this, the Q double prime is equal to H times, and again, assuming that this thing is being imposed inwards, times Ts minus Tm. Okay? So if we know the Q double prime, and we know the temperature Tm at the outlet, we can find TSO as long as we can find the H. And so now the trick is to find the H. So now we can't avoid the workflow, okay? So what is the workflow? Same deal that we did before. The first thing that we have to calculate is the Prandtl number. Now, I skipped a step, technically speaking, in the process of finding these material properties. Now it's important for me to highlight it, especially after we talked about how in external flow past cylinders and spheres, you know, there's this ambiguity about like how these properties vary with temperature. But the idea is that we have to decide some temperature at which I want to find the properties of this liquid that's flowing in here. And if we assume that that liquid is water, well, do we evaluate its properties at 290 or at 340? And the answer is neither. You try to evaluate them at the thing that is closest to an average, which in this case is literally just the average, 315 Kelvin. So all you would do is you would go into your textbook, you would find the properties of water at 315 Kelvin, and then write them down just like I did here. And in your book too, you can either manually calculate it by, you know, Cp times mu divided by K, or you could just look it up as well. You could find the Prandtl number of the water at 315 Kelvin, which is precisely the thing that is the first step. And so again, saving you the algebra, if I actually were to write down what the Prandtl number was for this particular system, if I did the algebra, I would get a very modest 4.16, right? So that's my first step. I have a Prandtl number. Now that I have a Prandtl number, I have to find a Reynolds number. So what is the Reynolds number? Now, the Reynolds numbers that we define for internal flow have to be defined not necessarily on the length of the conduit, but on the effective hydraulic diameter of the conduit. So if this was a circle, right, if this is a pipe, which it is, then the Reynolds number that I define is just rho times um times the diameter divided by mu. What is this um? It was that characteristic speed that I told you had been related to the mass flow rate and the volumetric flow rate by the cross-sectional area. Okay, and so the um that we use in this equation is just the volumetric flow rate divided by the cross-sectional area. But then this is also equal to the mass flow rate divided by the density times the cross-sectional area. Okay? And so we do have a speed. It's just that sometimes in internal flows, it's not quite obvious what that speed is because the speed is encoded in the mass flow rate. Okay? And so ultimately, we have to do a calculation that allows us to get from m dot to this characteristic speed. Right? And we know what the cross-sectional area of this is because from the perspective of what we're looking at, this is just a circle, right? So this cross-sectional area is just pi r squared, or pi d squared, pi d squared divided by 4. And so we know what this UM is. This d is just the diameter, and these are just the densities and dynamic viscosities, which we found off the table. But there's a thing that's interesting, which is what happens if in this exercise this was a square duct. What happens if the cross-section is not circular? Squares don't have a diameter, right? So what do we use? Well, in that scenario, what you would construct is this thing called a hydraulic diameter, which is this kind of effective diameter. It's almost like an average distance between edges of the conduit, right? And that hydraulic diameter is usually defined to be 4 times the cross-sectional area of the object divided by the perimeter. Okay, so if you have a square, you can find the cross-sectional area of a square, multiply it by 4, and then divide by the perimeter of the square. And you get this hydraulic diameter, and that's what you use to calculate the Reynolds number through this system. Okay? So, definitions aside, the point is that we know all of these things. For a standard pipe with a circular cross-section, the hydraulic diameter is, of course, just the diameter. This UM is just, as we had defined before, m dot divided by, some other things that got us to UM. We had written down that UM was equal to m dot divided by the density divided by the cross-sectional area. Right? So we know the cross-sectional area because we can find it. We know the diameter, we know the density, we know the mass flow rates, we know the dynamic viscosity, so we're all set. We can calculate the Reynolds number. We've got it. Once again, saving you math, the Reynolds number that we eventually find for this system is about 11,000. 11,119.84. Now, how much does the Reynolds number matter? How do we define the correlations that we use for internal flow, at least the common correlations that we use for internal flow? Well, one thing that we never talked about is how flow becomes laminar or turbulent inside of pipes. We had seen what happened in flow past flat plates. The idea was that after you went past a certain distance inside of the pipe, the flow transitioned from this nice orderly laminar flow into this chaotic, unsteady, turbulent flow. And as a result of that, the heat transfer that occurs in specific regions of that flat plate changes as you go from the leading edge of the plate. In the pipe, however, we have the fully developed assumption, where we assume that the nature of the flow past an entrance length, which is usually small relative to the pipe size, that flow doesn't change, at least not on average. And what that means is that there is a transition from laminarity to turbulence inside of pipe flows. It just happens everywhere at once. That is to say, if the Reynolds number is larger than some amount, you would see that the flow transitions from laminar everywhere to turbulent everywhere. And that makes sense because the Reynolds number that we're defining is a function of the diameter. It's not a function of x. So what is the usual criteria for turbulence inside of internal flows? Well, at least for these kind of like pipes, it's a reasonable approximation to say, at least from the perspective of a heat transfer course. If I was teaching fluid mechanics, which I do in the other semesters, you'd find that I would be a little bit more precise about this, but usually the idea is that there is a transition to turbulence that happens at around 2,300. So if the Reynolds number is larger than 2,300, then the flow is turbulent everywhere. If it's smaller, then it's laminar everywhere. Okay? And we clearly see that from the Reynolds number that we just calculated that this is much larger than 2,300. And so the flow is turbulent. how does that help us? Well, it helps us in terms of finding the correlation for the Nusselt number, right? And one thing that you should know about the Nusselt numbers is that, again, remember that we had concluded that the h's don't change. And so because the h's don't change, we also don't have to worry about locality, right? An h that I calculate here is going to be the same as the h that I calculate here. That being said, that's only true if we neglect the change of the flow that happens in the entrance region. But for most piping systems, it turns out that that entrance region is so small relative to the length of the actual conduit that we can neglect the correction that would happen by miscalculating the heat transfer in the entrance region, that we can just pretend like the flow is fully developed everywhere, and then off we go. So what is it? What do we do? Well, here are the 4 correlations that are used commonly to determine Nusselt numbers as a function of Reynolds numbers and Prandtl numbers inside of internal flows. This correlation is the correlation that you use to calculate the Nusselt number whenever the flow is laminar, represented with a curly L, and whenever the surface temperature of the pipe is a constant. Okay? And you notice that this is just a number. It's completely independent, technically speaking, on the Reynolds number and the Prandtl number. Now, is it actually independent? Not really, because in order for the flow to be laminar, the Reynolds number has to be lower than 2,300. So it kind of depends on the Reynolds number, but it doesn't show up. And so calculating the Nusselt number is super easy. You get a similar expression for laminar flow whenever you have a constant Q double prime. So this one was for when your surface temperature was constant. And now this is for constant heat flux. And you see that once again, the expression is constant. It's just a different number. Okay? In both of these scenarios, the flow is laminar. So what happens if the Reynolds number is larger than 2,300, which is what we got? Okay? Well, the correlation that we get is kind of interesting. It's a very interesting little correlation. So here it is. Okay? And it's 0.023 times the Reynolds number to the 4/5 power times the Prandtl number to an exponent n. And that exponent is different depending on whether or not the liquid inside of the pipe is heating up or cooling down, which is very weird, right? If the liquid goes from a lower temperature to a higher temperature, if that is the sort of process that's occurring in this pipe system, then we use an exponent of 0.4. If it turns out that the liquid is cooling down, then we use an exponent of 0.3. And so this is the correlation that we need to use because our flow is turbulent, okay? But which of these exponents do we choose? Well, we can clearly see the liquid is going from 290 to 340. So the liquid is heating up, and so therefore it's a heating process. So we use the 0.4. So all we have to do to get the Nusselt number is just plug in this Reynolds number, this Prandtl number, and 0.4 into this correlation to get the answer. And if we do that, once again, saving the algebra, in the interest of time and tidiness, there we go. The Nusselt number that we are going to get is approximately now I'm putting the average bar on it because this is technically average, but it doesn't matter if it's average or local, right? Because it's the same H everywhere. And so the Nusselt number that we get is about 70.185. So we have the Nusselt number, but how do we calculate the H? Simple. The same exact way that we did it before. We know that the Nusselt numbers are defined as H times D over K. We're using the D because remember that D is the length scale that shows up for this particular problem. Right? We used it for calculating the Reynolds number, so why wouldn't we use it for the Nusselt number too? So H times D divided by K will be our Nusselt number. We already know what that is. And so all we have to do is just say H is equal to the solved form of that equation, which is just the Nusselt number K divided by D. And we know the K, we know the D. So simplifying this up or making the calculation, we find that this is approximately 1,483 watts per meter squared Kelvin. Now that we've got the H, everything has simplified. Like we don't have to worry about the correlations. This is just now standard heat transfer modeling. Or all we have to do now is just say, well, Q double prime, right, is equal to H times TS minus TM, right? We found what the Q double prime was already. We just calculated the H. We know what the temperature of the liquid is at the outlet, it's 340 Kelvin. So now, if we know this, this, and this, we can solve for TSO. And so, moving everything around, right, once again, skipping the algebra, we are now left with enough to be able to solve for that temperature. And that temperature is approximately 389.42 Kelvin. There we are. And so if you were an engineer designing the system, you have to make sure that whatever material you make the surface of this pipe to be, that it can tolerate a temperature of 389.42 Kelvin without like warping or deforming significantly or anything like that. And so what are the different variations of things that could have happened in this particular setup? Well, we could have had laminar flow. In that case, if we had a laminar flow, we would have had to decide between these two, and we would have used this one because, of course, we have a constant heat flux that's applied. If we had a situation where we had a constant surface temperature, then, well, we would have used this one, but we also would have had to spend a little bit more time trying to figure out how the temperature varies in the system, because maybe, you know, the TSO would be easy because the TS would be constant, but maybe we would have some kind of missing information about the TMs that would make the problem considerably harder. But that's not something that we need to worry about now. The important thing is to know what the workflow is. That the idea is always with convection problems to find a Prandtl number, to find a Reynolds number, and to use the qualities of the flow to find the appropriate correlation to get you a Nusselt number and by extension an H. And after that, it's simple thermal modeling. So this concludes everything that we want to talk about, at least from the conceptual perspective, regarding forced convection, systems where we have an imposed flow, and that imposed flow affects the way that heat is transferred inside of the system. But we haven't covered a specific scenario where what happens when the fact that there is a thermal energy transfer, the fact that there are varying temperatures, could affect the flow. And so you can imagine a feedback loop where maybe the fact that there's a temperature difference causes a flow, and then the fact that there's a flow affects the heat transfer, which affects the temperature difference, which affects the flow, and so on and so on. And this leads to a new class of physical system, a type of physical system that is much more complex to study, which is usually referred to with the name of free convection. And we'll take a brief look at that in the next lecture, although we will try to avoid spending too much time on them just because of the fact that the correlations and the workflow become less and less clear the more and more complex the kind of energy coupling becomes. So we'll talk about it for sure. We'll discuss an example, or at least a simple example, and the parameters that govern how that energy coupling occurs, but we certainly won't be looking at it with as much detail as this. So we'll talk about free convection in the next lecture.